So this was a definite integration. For this, once again, sometimes it looks more difficult than it is. My u here would be 3 over x. That's what I'm going to use as u. So if I'm taking the derivative of that, you can write this 3x to the negative 1, right? So my derivative of that would be negative 3x to the negative 2, right? Another way to write that is negative 3 over x squared dx. If you look, I pretty much have all of that except the negative, right? I have, except the negative 3. I have the 1 over x squared right here. The only thing I have to count for is this negative 3, right? So my du equals negative 3 over x squared. If you think of this, this is 1 over x squared times e to the 3 over x, right? Does everybody see that? So I have the 1 over x squared. I just need to get rid of that negative 3. So I just multiply both sides by negative 1/3. So negative 1/3 du would give me my 1 over x squared dx, which would take care of this piece and this piece, right? Does everybody see that? So my u is 3 over x. My du is negative 3 over x squared. I need 1 over x squared divided by negative 3, right? And so now I can rewrite this to negative 1/3, 1 to 3 of e to the u, du. When I take this antiderivative, I'm going to get negative 1/3 e to the 3 over x from 1 to 3. I was just showing how you're replacing each piece of it. So I replaced this piece with u. I replaced these two with negative 1/3 du. So I've replaced every piece of it to do my substitution there. You don't have to rewrite it as u. If you've accounted for that 3, you can just go straight to the 3 over x. You don't have to. I was just showing every piece of it. You don't have to do this step. Since this is a definite integration, we should actually have a number here. So I'm going to keep going and say negative 1/3 e to the 3 over 3 minus e to the 3 over 1. And then you actually can plug that in and get a decimal if you want to. Or you can, leave it negative 1/3 e minus e cubed, or you can take an e out. Like, it depends on how it wants it. If it says round to the nearest whatever, plug it into your calculator and get a decimal. My u is going to be negative x squared. My du is going to be negative 2x dx, all right? So I have e to the negative x squared, and I have x dx, right? So this part of it, I can write as e to the u, right? That takes care of that. X dx, I have a negative 2x dx. So this is where I would say, well, negative 1/2 du would take care of x dx, right? So then I can replace this x dx with negative 1/2 du. And that's every single piece of my original. And of course you want to write it a little prettier, right? Negative 1/2 can come out. And then that's an easy antiderivative. I just have the antiderivative e to the u is just e to the u. So negative 1/2 e to the u from 0 to 1, but I do need to replace that guy with my u. So I would say negative 1/2 e to the negative x squared from 0 to 1. Then just plug it in. Negative 1/2 e to the negative 1 squared is just to the negative 1 minus e to the negative 0 squared. That's just 0, which is just 1. So then you can just plug it into your calculator, like I said, if they want you to do it, or you could actually just rewrite it. I think in the answer they probably pull out a negative, but that's okay. Negative 1/2 1 over e minus 1, something like that. bases other than e. So let's first look at the definition. If a is a positive real number and a does not equal 1 and x is any real number, then the exponential function to the base a is denoted by a to the x. So here we have a to the x equals e natural log of a times x. So these rules would apply to natural log and common log base 10. But honestly, these rules apply to all of them. So just like I mentioned with the e, anything to the 0 power is 1. Any base, you're going to add if you're multiplying like bases. You're going to subtract if you're dividing like bases. You're going to multiply them, the exponents, if it's a power to a power. The half-life of carbon-14 is about 5,730 years, which means it takes that many years for however much you started with the cut in half. Like, y'all would have done this probably in chemistry, half-lives. So if 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? Half-lives will always have a base of 1/2. That's the point of a half-life. So your half-life, by the way, if you ever get this question, your half-life function will always be a base of 1/2 raised to the power of the number of years it takes to cut in half, right? So t is the time that you've had over the half-life, however many years it takes for it to cut in half, which would, in this case, would be 5,730. It's always going to be your function for a half-life. So if they want to know how much will be present in 10,000 years, you're literally just going to plug in your 10,000 there. Assuming you started with 1 gram, obviously, because this is the half-life. You have to multiply your initial. So think of it like as e to the RT. Your initial times your what's happening to it. So initially they're going to say 1 gram. If that had been more than 1 gram, we would multiply by something different than 1. 1 gram is multiplied by the half-life. Half-life to the power is time, t in years, divided by how many years it takes for it to cut in half, the half-life of that particular unit that it's talking about. So I'm just going to plug in the years. That's all I'm going to have to do here. So in 10,000 years, it's going to be whatever this number is, right? Which is approximately 0.3 grams. Definition of a logarithmic function to base a. If a is a positive real number, then the log base a of x equals 1 over the natural log of a, natural log of x. Okay, this is actually the change of base formula. We don't call it that, but in pre-cal worlds, we did change of base. If you'll remember, if you have log base a of some number, you can do the natural log or common log, by the way, natural log of the x over natural log of the base. That's change of base. That's all that is. Like that's all that is. They're just writing it out that way. Properties of logarithms, any base. So this is just rewriting it, remember? So exponential can be written as a log. So the base of the exponent is the base of the log. The exponent is what you're actually finding, and the y is the value that you get if you were to take something to that power. So this is just the rewriting of the logs. We've done this before. Any base will cancel out any base. So an exponential base will cancel out a log base of the same log, and any log base will cancel out the same exponential base. So just like natural log cancels out e, and e cancels out natural log, any base will do that with each other. So that's all they're telling us here. Solving. Honestly, solving is easiest when it's an exponential form. 3 to what power equals 1 over 81. Remember, if you go to a fraction, it's a negative power. That's how I'll put it in the denominator. So you could just say, well, 3 to the 4th power gives me 81. So 3 to the negative 4th power would give me 1 over 81. So here x is going to equal that negative 4 because we're solving for the exponent. We're solving for the exponent here as well. So, I mean, this is the exponent. We're solving for what it would be. So rewrite it. So we're saying, well, 2, this is my exponent, to the negative 4th equals what? Just rewrite it if you don't understand the log. Our brains will naturally do the exponent faster in that form because we're so used to it. We've been doing exponents since we were in middle school. And so we're saying, well, 2 to the 4th power, well, that's 16. So 2 to the negative 4th power, well, that would be 1 over 16. All right, top of page 353. Derivatives. So the derivative of some base other than e to the x is going to be the natural log of that number, of that base, times that a to the x. This is actually the same thing as the e, but natural log of e is just 1. So that's why we didn't have to write that piece when it was a base e. This is actually the rule for any base, even if it were base e. But for base e, that natural log of e just lends itself to 1 times a number. If you have a to u, that means some function. So instead of just a to x, we have a to x squared. Well, it's still going to be the natural log of the base times that a to the x squared times the derivative of that exponent, 2x, right? So this is just, these two are the same. It's just we have to account for something other than x. The derivative of x is just 1, so there's no reason to multiply by 1. But the derivative of anything other than x is going to actually give us something else. Then look at derivative of logs from a different base. Log base a. It's 1 over the natural log of a times x. If this were a natural log, remember it was just 1 over x. But when you have a different base, you have to account for that log of that base. Same thing here. If it's other than x, then you have to do the derivative here. They give the proof. And they use it using your natural log. So these are the same as the natural logs. We just have to account for what happens after that. So if I'm taking the derivative, this is the derivative of something other than a base e. I have to say, well, the natural log of my base, that's ln of 2, times just my original function 2 to the x. That's my derivative. All right, let's look at the next one. Natural log then, so if I'm doing the derivative, natural log of my base times my original function. And then this one, because it's something other than x, we have to do times the derivative of 3x. We would probably rewrite this one. We would probably say 3 ln of 2. Put it in parentheses so you don't confuse it with the base 2 to the 3x. For the last one, if I'm doing the derivative, for this one, this is the derivative of a log other than base e. So I have to do 1 over the natural log of my base. That's the first piece of it. In the denominator, we also have what I'm taking the log of. So natural log of 10 times the cosine of x. And then I have to multiply by the derivative of this cosine, so times the negative sine of x. So I have negative sine of x over natural log of 10 cosine of x. There's another right way to write negative sine over cosine. What is sine over cosine? Tangent. It's tangent. So I can say, well, that's negative 1 over the natural log of 10 times the tangent of x. Or you could say negative tangent of x over natural log of 10, whichever way you want to write it. My antiderivative of a to the x is going to be a to the x, just like it was an e, but we also have to do 1 over the natural log of that a, of that base. Again, we didn't have to do this with e because natural log of e is just 1. So if I wanted to do the derivative then of this, or excuse me, the antiderivative of this, then I'm going to say, well, that's going to be 1 over the natural log of my base being 2, times my original function plus c. All right, power rule says let n be any real number, let u be differentiable in the function. We already know x to the n. The derivative of that is multiply by your exponent, subtract 1 from your exponent. So this one we already know. It's easy. Let's say I have a function to a power. Same thing here. We do the same thing with the function. So how does this affect it when we start getting things like this? Our biggest problem is sometimes we make e and we think it's a variable. And it's not. You have to like keep reminding yourself that e is a number. And so like this first one, e to the e power, that would be like saying the derivative of 3 to the third power. That's just a constant. And so the derivative of any constant is 0. We're done. There was no variable in here. So the derivative of a number is just 0. Here we have a number to a power. Well, the derivative of a number to the power of x is just going to be the derivative there, e to the x. So even if this had been any base to a power, we would have done that. We would have just done the natural log thrown in there. But this is e to the power, so e to the x. Now let's say we have x to the e. Well, that's like saying x to the third power. What would I do with x to the third power? Well, I'd multiply by 3 and subtract 1. This is x to the e power. E is just a number. So I'm going to multiply by e and make it x to the e minus 1. All right. Let's look at this. Y equals x to the x power. X to the x power. In this case, I'm going to use my natural log to help me with this, because this is the only one. Oh, this is the only one that's a little bit weird. The other ones just kind of make sense. This guy, we're actually going to have to work out. So for this one, we are going to take the natural log of both sides, just like we would when we did in our last section where we did the natural log to help us. Natural log of both sides. So now when I take the derivative, well, the derivative of this is going to be the derivative of that y over my original function of y. All right. On this side, I can expand, right? So before I take the derivative here, I'm going to expand. My exponent can go in front, right? So I have x ln of x. All right. This makes my life easier because now I can just use product rule over here. The derivative of the first one, well, derivative of x is just 1 times the second. So I have the natural log of x. Plus the first one, that's just x. Derivative of the second, well, the derivative of ln of x is 1 over x, right? So then I have y over y prime equals, this is just 1. So we have the natural log of x plus 1. Well, I need to multiply both sides by y, right? Because I'm really solving for this y prime. So we're going to multiply this side by y. On this side, when I multiply by y, remember I want to multiply by my original what y was. Y was x to the x power. So my derivative is going to be that x to the x power times the natural log of x plus 1. And that's really as simple as I can get that. I can't get that any simpler. I mean, I could distribute that x to the x through, but it doesn't really help me to do that. So I'm done.
interest. A limit involving e. So if we have a limit as x approaches infinity of 1 plus 1 over x to the x. This just went from here to here. They just got a common denominator. So 1 over 1, and they multiply both sides by x, right? So this is just getting a common denominator inside the parentheses. But if you have your limit as x approaches infinity of this guy, you get e. By the way, that is where they come up with this compound interest. So this is your compound interest. Your principal times 1 plus your rate over the number of times you compound raised to the number of times the number of years, right? That's your compound interest. So how did they get from here to here? The PERT, which is the formula we all remember. Continuously compounding means your number of times per year is moving towards infinity. Number of times per year is moving towards infinity. That's how they got this e to the RT, okay? So that's how they went from this formula to this formula. It's this limit theorem right here. So if you are compounding 4 times a year, we're going to use this guy right here. But if you're compounding continuously, you're going to use this guy. And they got PERT from this formula using a limit theory saying n is moving to infinity. That's what they did. So that should be very familiar. And this should feel like just the easiest thing in the world right here. $2,500 deposit is made in an account that pays an annual interest rate of 5%. Find the balance on the account at the end of 5 years if the interest is compounded quarterly, monthly, continuously. So if I did that, I would say $2,500 is my initial amount. 1 plus my rate in decimals, 0.05, over the number of times I compound quarterly is 4, raised to the number of times I compound by the number of years. That would be 4 times a year. If I wanted to do it monthly, I would use this one, 12 times a year. And then if I wanted to do it continuously, it would just be the PERT, 25,000 e to the RT. All right. So hopefully we know all of those and we're familiar with them. Typically when they give you a bacterial, either they'll say it's continuous and they'll give you like an initial starting one and it works out to e to the RT, or they'll give you a formula. The bacterial growth is growing according to this growth function, and they give you the growth function. Y is the weight of the culture in grams, T is the time in hours. Find the weight after 0 hours, 1 hour, 10 hours. Well, you're just literally plugging in 0, 1, and 10 into your time. And then they say, well, what happens if this were to go continually as T approaches infinity? And that's really the only one that we want to talk about, because the other, I think you can just plug in a T and figure it out, right? But if it were to go continually, then you have this number negative to a negative power continuously. This guy's getting significantly smaller, because if you think about it this way, we have 1/4 times 1 over e to this power. So this piece of it is getting significantly smaller. My numerator is staying a 1. My denominator is growing exponentially. E is taken to a power. And so this is going to move towards 0 right there. So I'm going to end up with 1.25 on the top and 1 plus 0 on the bottom. This guy is moving towards 1.25. Okay, so when you think about a question like that, what happens if it moves towards infinity? Then you just apply your limit rules. Like, what happens if a fraction's denominator grows infinitely? Well, it's moving towards 0 because it's getting to be tiny, 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 tiny fraction. So what's happening as the limit approaches that fraction is approaching 0. That's what they're asking here for this last one. As t approaches infinity. Well, as t approaches infinity, this piece of it on the denominator side, that little piece is approaching 0. So logically what's happening is it's moving towards 125. This is asking as t approaches infinity. So as t approaches infinity, which means this is getting infinitely larger, which means the denominator is making that fraction get smaller, right? If I have 1 over a little tiny number, that's a big fraction. But as that denominator gets bigger and bigger, it's moving towards 0. So if I'm moving towards infinity, this piece is just going to 0 out. That's just going to 0 out. The 1's not going to change as it moves towards infinity because it doesn't have a t in it. The numerator's not going to change. It doesn't have a t in it. The only thing that has a t is this piece right here. Now, if this were not to a negative power, that's not necessarily the case, right? If this were a positive power, then the whole denominator would be getting big and my numerator would stay. So the whole thing would be moving towards 0. But this piece of it is moving towards 0 because of that negative exponent.